Aloha! In this 7th lecture in our Acids and Bases series, we discuss conjugate weak pairs. Before we say what those are and how they're related to acids and bases, let's begin with an interesting observation. I've drawn here schematics of 4 solutions. The first one is 1 molarity sodium fluoride, the second 1 molarity sodium chloride, third 1 molarity sodium bromide, and the fourth 1 molarity sodium iodide. So the cations are all the same, the concentrations are all the same, but the anions are different. Now, if you take a pH meter and you measure the pH of all 4 of these solutions in the laboratory, what you would find is the first one is slightly basic with a pH of 8.08, while the other 3 are neutral. So the question is, why is this the only one that's basic? To help answer that question, it might be appropriate to take a look at the other ones and see why they are neutral. And if we can understand that, then I think you'll see why the first one is slightly basic. So these other 3 are neutral solutions. Now, take a look at the anions of these solutions. Do you see what they have in common? They are all the conjugate base anions of strong acids. Hydrochloric acid, when it dissociates, gives chloride in solution. Hydrobromic acid is also strong, and it gives bromides, and hydroiodic acid gives iodides. So these are the anions that are released from strong acids. On the other hand, fluoride is the conjugate base anion of hydrofluoric acid, which is a weak acid. And that's the main difference here. This one contains an anion that's the conjugate base anion of a weak acid, and that's what makes this solution slightly basic. To see a little bit better why that's the case, why the anion of a weak acid is basic, but the anions of strong acids are not, let's compare hydrochloric acid and hydrofluoric acid. So I've drawn written the chemical equations for what those acids do when they're in solution. First, hydrochloric acid. Let's see what that one does. Hydrochloric acid is one of the 6 strong acids, and like all strong acids do, it fully dissociates in solution, as acknowledged by this one-way arrow here. So all of the HCl molecules will dissociate into protons and chloride minus anions. This reaction goes in one direction. You will not see the product ions combining back together to reform the reactant. It doesn't go in the other direction. So once this dissociates, the product ions stay that way. So I like to think of this chloride as being comfortable in solution. It's not looking to do anything, it's good. Now let's consider hydrofluoric acid. This is one of the many weak acids out there, and weak acids also dissociate into protons in the conjugate bases, but it's a partial dissociation. And on top of that, the equilibrium lies heavily to the left. Most of the hydrofluoric acid will be undissociated in solution. Only a small fraction will be in the form of protons and fluorides. And equilibrium reactions go in both directions. So at equilibrium, the reaction's still occurring in the forward direction and also the reverse direction, but just at equal rates. And so the concentrations remain the same at equilibrium. But these product ions are constantly recombining to reform the original acid, and other acid molecules are dissociating. So the equilibrium is still occurring. And so you could think of this fluoride as looking around for a proton to combine with to reform the acid. So this is not so comfortable in solution. It's looking to bond with a proton, or you could say it's looking to accept a proton. And we know that substances that accept protons in solution are basic. So hopefully you see why the chloride is neutral. It's comfortable in solution. It doesn't want any protons, but the fluoride is basic. It wants to combine with protons. So to sum it up a little bit, the conjugate base anions of strong acids are neutral, while those of weak acids are basic, and they're weakly basic. Now, if they are basic, if anions like fluoride are weak bases, then they must have KBs. Remember, weak acids have Kas and weak bases have KBs. However, if you go to your Gen Chem text appendix where the list of KBs for common weak bases are, you won't find this one. I would almost guarantee you that you won't find that one. And it's not because the appendix isn't big enough. There's another reason. So how do we find the KBs of weak base anions like this? Well, I'll give you a quick clue and then we'll explain it. It's related to the Ka of its conjugate HF. So in another part of the appendix, you'll see the list of Kas, and you will find the Ka for HF. And if you can find that, then there's a simple equation that lets you calculate the Kb for F minus. So let's see how that works. Now this works for any weak conjugate pair, so we'll just choose F minus and HF as our weak conjugate pair to illustrate this simple equation that relates Ka and Kb for weak conjugate pairs. So we'll use HF and F minus. Now hydrofluoric acid is an acid, and it's a weak acid, so it undergoes dissociation, partial dissociation. And this equilibrium corresponds with the equilibrium constant expression over here to the left, outlined in red. So Ka, since it's an acid, equals the product concentrations over the reactant concentration. And of course, water is a pure liquid, it's not included. So that's the acid equilibrium. Now let's look at the base, F minus. Now it's a weak base, and weak bases also undergo equilibria, but they produce hydroxides. So this F minus takes a proton from water to reform HF and leaving hydroxide. So that's the base equilibria, and the equilibrium constant expression for it, Kb this time, equals the product concentrations over the reactant concentration. Now, what you do is you take these two chemical equations and you add them together. And you probably remember when you do that, you add all the products. So those will be all on the right. There are 4 of them. And all the reactants, they're on the left. So this is the sum reaction. Now look at all of the species that are down here in this sum equation. Let me show you the rest of it. Sorry about that. This is the total reaction. Notice that the HF is on the left and on the right. So you can cancel that off if you want to. And also F minus is on the left and on the right. And if you cancel off those species, what you're left with is water dissociating into protons and hydroxides. What you're left with is the autoionization of water reaction. Now, the equilibrium constant for this, the autoionization of water, that's Kw. So the equilibrium constant for this should be Kw. Now let's go ahead and uncancel those HFs and F minus and just write the equilibrium constant with everything in there without canceling it off yet. Okay, so you have 4 product concentrations, they're all up there, and then these 2 concentrations are down there, and water, of course, doesn't need to be included. Now, here, the equilibrium constant for that total reaction, we'll call it Kw for the moment, you can see that these 3 terms on the left, those are your Ka terms. Okay, so that right there is Ka. And those three on the right are the Kb terms. So really, you can see how this equilibrium constant expression is really Ka times Kb. Now also, if you now cancel off the F minus up here and down there and the HF up here and down there, you'll see that this equilibrium constant is also the proton times the hydroxide concentration, which is Kw. So that's the big relation. Ka times Kb equals Kw. And maybe you could have thought about this a different way. When you add two reactions, the equilibrium constant of the sum reaction is the product of the two equilibrium constants that you're adding. And so the equilibrium constant for this reaction, which we see as the autoionization of water, is simply, which is Kw, must be Ka times Kb. So a couple of ways to see the relation between Ka and Kb and Kw. So this is our big equation right here. Ka times Kb equals Kw. And of course, for water at 25 Celsius, Kw is 1 times 10 to the minus 14. So to answer the original question, how do we find the Kb of the F minus anion? Well, we look up the Ka of HF, and we can find that pretty easily. And then if we solve this for Kb, we can calculate Kb as Kw over Ka. So we don't have to have Kb in the appendix because it's simply Kw, which is that, over Ka. So let's do that. In this example, you're asked to find the Kb of the weak base anion fluoride minus at 25 Celsius. And you look up in the appendix and you find its conjugate, HF. That's what's available. You won't find the Kb of F minus, but you'll find the Ka of HF, and it's 6.8 times 10 to the minus 4. And so using this equation to solve for Kb and plugging in Kw and the Ka that is in the appendix, you can calculate what Kb is, and it's 1.5 times 10 to the minus 11. So it's pretty small. Now, let's do another example where we use that relation. Okay, here we go. This one's a little more involved. You're asked to find the pH of the solution formed by dissolving 100 grams of potassium hypochlorite, that's KClO, and 2.5 liters of solution. Now, potassium hypochlorite, KClO, is an ionic compound. You have your metal cation and your non-metal anion. This is one of those oxyanions. So potassium hypochlorite is an ionic compound. And you can see right here what it does. Like all ionic compounds that are in solution, this one is fully dissociated into its metal cations and non-metal anions. Now, forget about the cation. That does not affect the pH. This is a neutral cation. We'll see in the next video that certain metal cations, if they're highly charged, can affect the pH. They can make it acidic. But if you're just dealing with +1 cations or +2 cations that are small, then they're not going to affect the pH hardly at all. Okay, so insignificant. The other anion, on the other hand, the hypochlorite anion, is a basic anion. Now, how do we know it's basic? Well, of course, if you ask about its conjugate, HClO, that's a weak acid. And since this is the conjugate base anion of a weak acid, that makes this a basic anion. Another way to remember that this is a basic anion is simply to memorize the list of neutral anions. So these are the anions that are neutral. There are 6 strong acids, but there are only 5 anions here. And that's because that other strong acid, sulfuric acid, When it dissociates, that leaves, H2SO4 dissociates into H plus and HSO4 minus, and that HSO4 minus still has one more proton that it can release. So that's an interesting case. Sulfuric acid, its conjugate base anion is actually slightly acidic, and so there are really 5 neutral anions. So this is not one of them. That means this is a basic anion. Now, you're asked to find the pH of this solution. It tells you how much of the potassium hypochlorite is in there in the volume. And so if we could figure out the concentration of the hypochlorite anion, then what we would do is write the base equilibria that the hypochlorite anion undergoes and use its concentration right there as the initial concentration and fill out the ice diagram and then solve for the hydroxide concentration. Since this is a weak base, the ice table, when you solve for X, that will give you the hydroxide concentration. And then you can get the POH and the pH. So there's a lot of steps here. Let's just go through them carefully. First we need the concentration of the hypochlorite anion. We're told 100 grams of potassium hypochlorite is in 2.5 liters of solution. So what is the molarity of the hypochlorite anion? How do we get that? Well, we do that right down here. To find the initial hypochlorite concentration, we take our 100 grams of potassium hypochlorite and convert that to moles using the molar mass of potassium hypochlorite. So upstairs is the moles of potassium hypochlorite, and if you divide that by the liters of solution, it's 2.5 liters, you will calculate the molarity of the potassium hypochlorite. It's 0.442 molarity. Now, that's the molarity of potassium hypochlorite, but remember that potassium hypochlorite dissociates into its potassium ions and hypochlorite anions. And one of these formula units gives you one of those. So if there is 0.442 molarity of potassium hypochlorite, then that means there's 0.442 molarity of the hypochlorite. And so that's our initial concentration right there. So here we go, that's our starting point. We don't have any products at the beginning. We're ignoring autoionization of water as we normally do. And so to get to equilibrium, we lose X amount here and gain X amount there and there. And so 0.442 minus X and X and X. And these equilibrium concentrations can be plugged into the equilibrium constant expression for this weak base. It's Kb equals the product concentrations over the reactant concentration. And so that's your Kb expression. The concentrations are plugged in over here. And the Kb for hypochlorite, since this is a conjugate base anion, you can't find it in the appendix. But you can find the Ka of its conjugate, and that's 2.9 times 10 to the minus 8. So remember, we can solve for Kb using this equation over here. Kb is Kw over Ka. So to put this all together, we plug in these equilibrium concentrations into the expression, and that's what we have right here. And then Kb over Ka is right there. That's your, Kw over Ka is right there. So that's your Kb. Now this big nasty looking expression, you can solve for X. You can solve it exactly, which might take a little bit of time, and you'll get 0.00039, or you can use the X's small approximation and get rid of that X right there, and you get 0.00039. So I would recommend the X's small approximation, but whatever suits you, just solve it. And so X is your hydroxide concentration. So we can now calculate the POH. That's negative log of the OH concentration, and that comes out to be 3.41. So that's your POH. So the pH is 14 minus the POH. So the pH is 10.59, and had that covered up right there. So the pH is 14 minus the pOH, which is 10.59. So kind of involved a little problem. Now let's do one more. And for this one, I decided to throw you a few curveballs. I hope you don't mind. I tried to make it somewhat challenging, so we'll have to take it slow and figure out how to do this. This problem right here is somewhat opposite to the one that we just worked on. Now, let's see, let's just read it. Suppose you want to find the pH of 0.1 molarity ammonium chloride in solution. And it's at 37 Celsius, which is body temperature. So find the pH of 0.1 molarity ammonium chloride at 37 Celsius. Okay, now at 37 Celsius, the pKb of ammonia, that's the conjugate base of this. So this would be the conjugate acid of that, and that would be the conjugate base of this. So, you're told the pKb of NH3 is 4.73, and the pKw of water at this temperature is 12.30. So what are these pKbs and pKws? Well, they're just like the pH and the pOH. The pH is the negative log of the H plus concentration, and the pKb is the negative log of the Kb. So you're told the pKb of NH3, so you can figure out what the Kb is. And likewise, you're told what the pKw of water at that temperature is, so you can figure out what the Kw of water at that temperature is. Maybe you remember the relation, with logarithms and power of 10. If the pKw of water is 12.30, then that means that the Kw of water is 10 to the negative 12.30. So there's a few things going on here. It's at a different temperature, which is a little complicated because we're dealing with a different Kw of water now. It's normally 10 to the minus 14, but now the Kw of water is 10 to the negative 12.3. So the Kw is a little bit greater this time. And also, the NH4 plus is a weak acid. Last time we were dealing with a weak base, and we had to look up the Ka of its conjugate. Now we're dealing with a weak acid ion, so we need the Kb of its conjugate. You see, conjugate acids of weak bases are acidic, just like conjugate bases of weak acids are acidic. When you have a weak conjugate pair, like NH3 and its conjugate acid NH4 plus, this the basic the base form of the pair is basic, and the acid form of the pair is acidic. So here you have the acid, and it tells you the Kb of its conjugate, and we can figure out what the Ka is of the acid. So a lot of words there, a lot of mumbo jumbo. Let's put it all together here. First, let's see what NH4 plus does. Being an acid, it establishes equilibria. It dissociates to a partial extent to form protons and ammonia in solution. So this donates a proton to water to give H3O plus, leaving the conjugate base ammonia. Now, if you have 0.1 molarity of NH4Cl, then you have 0.1 molarity of NH4 plus, and also 0.1 molarity of Cl, but that's neutral. So the initial concentration of the NH4 plus, the ammonium ion, is 0.1 molarity. And the proton we assume is 0, ignoring autoionization of water, and the ammonia is 0. So to reach equilibrium, the reactant loses a certain amount of concentration, X, and the products gain X amount of concentration. And so these are the equilibrium concentrations of all species. Now the equilibrium constant expression for this reaction is right here, the product concentrations over the reactant concentration. So you plug in these equilibrium concentrations over on the right, but what is Ka? How do we find Ka? It tells you, what pKb and pKw are. It doesn't tell you what Kb and Kw are. It tells you what pKb and pKw are. So how do we make sense of all that to figure out what Ka is? Well, let's start with the relation between Ka, Kb, and Kw. If you take the negative log of the left side and the right side, then the left side is the negative log of a product. So that's the negative log of the one plus the negative log of the other. And the negative log of Ka is pKa. The negative log of Kb is pKb. And so the negative log of the right side would be pKw. So you see pKa plus pKb equals pKw. And we derived that from that equation. Now, if we solve for pKa, it's going to be pKw minus pKb. Now, we're getting pretty close to Ka. pKa is pKw minus pKb. So if we make the left side, if we say 10 to the negative pKa, then we also have to say 10 to the negative all of that. 10 to the negative pKw minus pKb. Now, 10 to the negative pKa, that's simply Ka. Those are inverse operations. 10 to the negative pKa is Ka. Okay, just like 10 to the negative pH is the H plus concentration. 10 to the negative pKa is the Ka. So, over on the left, this becomes Ka, and over on the right, that's 10 to the negative all of that. So we have the pKw and pKb. Let's just put those in there, 12.30 and 4.73. So let's plug those in. That inside the parentheses is 7.57. So Ka is 10 to the negative 7.57, and that comes out to 2.7 times 10 to the negative 8. So that is the Ka of the NH4+, and that's what we plug in right here. So now that we have everything, here's our equation. We can solve for x. And you can use x's small approximation here because the initial concentration is much bigger than 1,000 times the equilibrium constant. So it's definitely safe to use x's small. You can ignore that x down here covered up. You can ignore it. And it would be easy to solve for x doing it that way. So x comes out to 1.6 times 10 to the minus 4. That is the proton concentration. I have a typo right here, okay? This is bugging me. X is the proton concentration. I say that it's a hydroxide concentration, but it's really the proton concentration. I wish I could cancel that out, but it's already burned in the video. So this is proton concentration. So the negative log of the proton concentration would be the pH. So that's what this is actually right here. If you take the negative log of that number, that's the pH, and that comes out to 3.79. So 3.79 is the pH. Okay, that's not, it's 3.79. It's a acidic solution. So there we go. That's a pretty involved couple problems right there. 3 of them, and I hope you were able to follow along well enough. In our next video, we will discuss small, highly charged metal cations, which act as acidic ions. So kind of interesting. The next lecture will be much shorter, just 1 page of notes. So stay tuned for that. Aloha.